on how you did the density was perfect, and then we ended up with 18.3 molarity. Okay, who wants to find molality for us? Come on. I know someone wants to do it. Molality is easy.
Just to clarify, molality, because sometimes I get, like, I have the right idea, but I get it wrong. Molality is the moles of solute over the kilograms of solvent.
Mm-hmm.
Okay, because that's what trips me up, is that I have
they're a
tendency
little
to want to do solution.
Yeah, I messed up on the molarity like that. I put liters of solvent. No.
Which at that point, it does help that he writes down the test, because if you have that moment during the test where you're like, oh my god, is it solution or solvent?
Yeah,
he does give it to you. So don't freak out. Go use the formula.
Nice.
You know how to use it. But yeah, molarity, moles of solute, total liters of solution. Molality is moles of solute, so same top, and then kilograms of solvent. So knowing that, who wants to find molality for us? It's the easier one, I promise. Molarity was all we did.
Okay.
What was your name?
Sarah.
Sarah?
Mm-hmm.
What's your name?
Kristen.
Right up top. You're on tall.
Sorry, my handwriting
No, you're
just...
fine.
I wrote really large. So
Oh, okay.
I don't know how to write small.
Yeah, me neither.
Okay, so we already decided that it was 2.05 moles of solid, and then solvent is the 75 grams of water, which is
Definitely don't forget the kilograms either.
yeah.
If you accidentally use grams, the whole decimal place is going to be in the wrong spot. It's kind of a weird unit.
Okay.
Perfect. Did everybody see how she did that? Yeah?
Yes.
That was the easier one in this case, because I already gave it to you in grams. You didn't have to add anything.
Okay.
Okay, who wants to try C for us?
There's a
Everybody
C?
C?
Oh.
No? We can ponder it together. Just walk me through how you would do it. Anyone?
This would be like the change in T problem, right?
I'm going to tell you now it's a trick question.
Okay.
I want someone to tell me why it's a trick question.
Because it says raise.
Oh.
You're allowed to talk.
You can go.
Molality is independent of temperature.
Ding, ding, ding.
Oh, that's what it means. Okay.
This is why we like molality. It's a super weird unit, but this is why we use it. It's because it doesn't depend on temperature.
I see. Okay.
Molarity does.
All
So, since it's liters of solution, density changes when you change temperature. So, water's not always 1 gram per milliliter. It changes. So, molarity means it changes with temperature, which means that we can't compare things between things, you know? So you can't always compare things directly using molarity. With molality, you can, because nothing changes. You still have the same moles, you still have the same kilograms, because mass does not change.
Okay.
Volume does. Does that kind of make sense?
Yes.
I don't anticipate him asking you this question. He's not really a trick question kind of guy.
Okay.
But I just want you to be aware that
Aware.
it was an important point in the PowerPoint.
Okay.
Okay, that's our review of Chapter 13. Know how to do this kind of thing. It's very important. He will ask you. It's the way it is. Okay, now we are moving back to Chapter 12. So like I was saying, Chapter 12 is not usually covered in this course. So I don't know exactly what he's going to ask you on the test. I'm going to talk to him and see if I can figure it out.
Thanks, that'd be
um,
awesome.
For next week.
Yeah.
But for now, I just want to go through the chapter and make sure you guys just kind of are getting it, because Chapter 12 is a really foundational chapter. He may not ask you a lot of questions directly from it, but if you get chapter 12, chapter 13 and 14, and all the rest of them are going to make a lot more sense.
Okay.
So it's a very concept-based chapter. It's not problem-based as much as the rest of the classes. So we're going to walk through some of that. Oh, and my name's Alyssa. I'm on the board, but I took this class 2 years ago and I loved it.
Oh, that's awesome.
I'm a biochem major and I love this stuff. So.
Well, I'm proud you can get through it in PEs.
I'm telling you, it really was one of my favorite classes freshman year.
That's
Did you
awesome.
take it with grade or? Okay.
Yeah, he's one of my favorite professors here. Okay, so the first part of chapter 13 was all about IMFs. Does anyone want to tell me what an IMF is?
Intermolecular forces.
As opposed to intra, right?
Oh, yeah.
So you guys have talked about intra before in Gen Chem 1. Intra is forces within a molecule, so something holding 2 atoms together.
Mm-hmm.
What would be some examples of that?
Dipole.
Mm.
Oh, no, wait. Covalent. something.
Yes,
There
we go.
I got confused.
Covalent's the biggest example of an intramolecular force, something that's holding a molecule together.
Mm-hmm.
We're going to talk about things like dipole-dipole
Right.
that are inter. So these are forces between different molecules.
Okay.
It's not within a molecule, it's between them. So this is how they interact with each other in solids, liquids, gases, everything we think about when we think chemistry, basically. So we started in class with dipole-dipole. What kind of molecules are involved in dipole-dipole interactions? Just give me really general, or you can give me an example. What kind of molecules would be involved in a dipole-dipole? What is a dipole? What does a dipole mean? You know?
NaCO. Wrong. Okay.
That's an ionic bond.
Okay.
So those are, we'll talk about that in a little bit, but
Okay.
not quite.
Is it polar?
Ah! Polar molecules.
Okay.
Polar molecules participate in dipole-dipole interactions.
Got it.
What a dipole is it basically means 2 poles. 2 poles that are separate from each other.
Oh,
Which
okay.
means we need 2 different things happening on each end, which is basically the definition of a polar molecule. A
Oh.
polar molecule is something that has a positive on one side and a negative on the other. Classic example, H2O. Oh, not 2 O's. In H2O, we have a much more electronegative atom up here, a much less down here, which means that oxygen is going to steal all of the electrons from the hydrogens, which is going to give it a partial negative charge. And by pulling away the electrons, the hydrogens are going to get partial positives.
Right.
This creates the polar effect, and it creates dipole-dipole interactions, because if we have, I don't know, maybe something like, now I can't think of anything, CO2. Let's say we have CO2. This is also going to have a partial negative, so these partial negatives are going to interact with each other. Yeah?
Mm-hmm.
So dipole-dipole interactions are interactions between 2 polar molecules. These won't happen between nonpolar molecules. You've got to have those partial charges. Nonpolar molecules aren't going to have the partial charges.
How do you tell, like, if it's polar or non-polar by looking at the structure?
You want to give me an example?
I don't know.
Okay, so this has to do with electronegativity. Have you guys talked about electronegativity? Yeah. So if you look at a periodic table, in general, have you guys talked about periodic trends? Kind of.
Yeah.
One?
That side is very electronegative, but the F,
Is
fluorine.
like the highest?
Yes.
Exactly. Yeah, fluorine's up in the corner here. It is the most electronegative molecule. However, if you look at a periodic table, the trend is that as you move up and to the right, things get more electronegative. So oxygen is really highly electronegative, nitrogen, all of the halogens are very electronegative over here. Anything up in this corner is going to be very electronegative. So when you have a bond between 2 atoms, basically, you want to look at their electronegativity difference. So when we look at, say, let's say H2O, hydrogen's way over here on the left side of the periodic table. It's electronegative because it's high, but it's not as electronegative as oxygen, which means that oxygen's still going to steal those over. What I would really look at when you're looking at if there's a dipole or not is look at your halogens and look at fluorine, oxygen, nitrogen. Those are the ones that are going to be the most common examples of having a big difference in electronegativity. So if you see like a hydrogen paired with any of these, you should expect a dipole.
Okay.
That's kind of where you should be thinking. The other thing to kind of think about is we talk about ionic bonds, and we talk about how, what is an ionic bond? Does anyone give me a definition about how electrons are moving within an ionic bond? Way back from Gen Chem 1.
Yeah.
So in a covalent bond, we share electrons, right? That's kind of the definition. Yeah?
Right.
So if we have, I don't know, I mean, basically anything.
They're
H2O,
pulling.
covalent bonds. They're sharing the electrons.
Right.
We do have these partial charges, but they're still sharing them. The electrons will still spend time over with hydrogen, even though they like oxygen better. With an ionic bond, so like NaCl, like you mentioned earlier, we get these ions, this ionic bond, because chlorine basically steals the whole electron pair from sodium. Why is that? It's because sodium's way over here. Sodium doesn't have a very good pull on these electrons, so when Cl comes in and makes a bond with it, it basically steals most of them over. An ionic bond is basically the most extreme example of a dipole bond, right? Because it's basically just taking this partial charge to the whole next level. So if you think of anything that you've thought of as ionic compounds, think of them as like the extreme dipole compounds, and then you can kind of come back and say, well, those are ionic, but if we have something like HCl, maybe that can be a dipole, because it's similar, but it's still got the bond. Does that kind of make sense?
Kind of, yeah.
It's a lot of just looking at structures. Like, so that's the basis of it, and then if you start looking at things like, I don't know, CH3, would you call that polar or non-polar?
That would be polar
Why would it be polar?
because it's non-symmetrical.
The symmetrical is non-polar, right?
Symmetrical, if something is symmetrical, it's almost always non-polar. However, it doesn't have to be symmetrical to be non-polar. This is polar, but why is it polar? Not because it's non-symmetrical. Look at the electronegativity. What's going on?
Oxygen.
Mm-hmm.
Oxygen is very electronegative,
Oh, okay.
and the hydrogen is not. So
Yeah, we're gonna get some dipole moments going on over there. To give you an example of something that would also be non-polar, that isn't symmetrical.
Okay.
What about this?
This would be.
it's not polar.
Non-polar.
Yeah.
Yeah.
Non-polar.
It's non-polar because even though you will have some polarity going on in this bond, because oxygen will want more of the electrons than carbon will, even though there's some polarity going on, there's not going to be the kind that's going to influence the whole molecule,
Right.
if that makes sense. Is there any hydrogen bonding happening in that bottom one?
No,
Why not?
Yeah. Well, wait.
because there's no hydrogen bonded with nitrogen, oxygen, or fluorine.
There's no hydrogen bond going on here because even though there's a hydrogen and there's an oxygen, they are not attached to each other, which means that they cannot create hydrogen bonding between each other.
Okay.
And with that, I'm kind of getting ahead of myself, but we will come back to this.
Okay.
There's no hydrogen bonding happening here. You have to have hydrogen attached to one of those three molecules.
God.
Fluorine, oxygen, nitrogen.
Right.
We can come back to this if this is still confusing. We can try more polar or non-polar examples. Let's keep moving though to see if other things can help fill in the picture. Okay, so dipole. Big intermolecular force, very important to know. The other big one we talked about were London forces, or London dispersion forces.
This happens in every single molecule.
Mm-hmm. And that's very important to know. London dispersion forces happen in every single molecule. You will not find a molecule without London dispersion forces.
Right.
We talk about them being in nonpolar molecules. The only reason we say that, though, is because this is the strongest force in nonpolar molecules because there's no dipole-dipole force.
Mm-hmm.
So even though we talk about nonpolar, polar molecules also experience this. It's just so much weaker than dipole-dipole. We usually don't talk about it a whole lot because the dipole-dipole is what influences the molecule more, basically.
Okay.
But it happens everywhere. You're right. Everywhere.
Okay.
So keep that in mind. If he ever has you, like if he gives you a bunch of molecules and says what intermolecular forces do these experience,
Right.
then make sure you always put London dispersion forces.
Yeah.
Sometimes they're just called dispersion forces, sometimes they're called London forces. Any combination of these words is basically it. Okay, so then the last one that we talked about in the PowerPoint were hydrogen bonds, which are very important bonds that will come back to haunt you in every chemistry class you ever take. So, is hydrogen bond an example of London forces or dipole-dipole forces?
London. No.
Mm-hmm.
Okay.
It's an example of dipole-dipole, purely because of this. Like, this is a dipole-dipole bond, but more specifically, it's a hydrogen bond. It's both. So hydrogen bonds can be seen as a subset of dipole-dipole bonds. They're super strong dipole-dipole bonds.
Okay.
This is as strong as a dipole-dipole bond gets, but it is an example of them. Hydrogen bonds. Whenever you think of hydrogen bonds, think of having fun, because you're having fun. A teacher told me that once and it stuck with me.
Yeah.
So whenever you're trying to remember what molecules hydrogen bond, you want to have fun. So those are the only 3 molecules that will ever hydrogen bond. Don't try to be doing HCl, don't try to be doing any other bonds with hydrogen and say it's hydrogen bond, because it's not.
Okay.
Only those 3. It's very strong dipole-dipole, like we talked about, so it's the same kind of interactions with other molecules that we were talking about, how you have the negative and the positive ends, and then they orient themselves so that they're with other positive and negative ends. So Dr. Steffen was teaching when we were doing this, and she mentioned a couple things that were important with hydrogen bonds. One of them is that hydrogen bonds are strong, but when you look at them in solution, you have to think about how many there are. So her example was H2O versus HF. So when you're looking at the having fun here, the fun is actually in order of the electronegativity of those ions. So fluorine is actually more electronegativity than oxygen. So an HF bond is stronger than an HO bond, if that makes sense. However, even though that's true, the intermolecular forces in H2O are still stronger because there's more going on. You've got more lone pairs and hydrogens to bond with other molecules. Whereas with HF, you have this bonding somewhere, and then you have this bonding somewhere, and that's it. So there's 4 hydrogen bonds for each H2O and only 2 for each HF. So even though this is a stronger bond, H2O still has a higher boiling point. And we'll talk about boiling point, but boiling points, they're higher when there's more intermolecular forces. I don't know if you guys have read the chapter, but they kind of went into that a little bit, and she mentioned that the boiling points of these two. So this will have a higher boiling point, water will, than HF because of those extra bonds. So that's an important part of hydrogen bonding. And then the other part was just something to be aware of what a hydrogen bond donor is versus an acceptor. So is this a hydrogen bond donor or acceptor? What do you think?
Acceptor.
Oh, it can't be both?
Why is it both?
Well, like if you have several water molecules, you can have an H molecule bond to that O, and then you can also have an O bonding with the
Yeah, that's exactly
Wow,
right. Uh-huh. So this plus here is going to be bonding with a negative over there, and this negative, these lone pairs up here are going to be trying to bond with hydrogens out there. So this is a donor and an acceptor. Something to be aware of, you can have one without the other.
Okay.
So one example is nitrogen. If you put this compound in water, nitrogen's going to have a slightly negative charge because it's going to be pulling in electrons from the carbons. This hydrogen's going to have a slight positive charge. This is a hydrogen bond. Even though this isn't donating anything, it can still be an acceptor. Something to be aware of. I doubt it'll ever come up directly as a problem, but just be aware that there's lots of interactions going on between molecules, and they don't have to be everything to still be doing something. Let's see. Okay, so are there any questions about that?
So the more hydrogen bond you have, like, the more you have.
The more intermolecular forces there are.
Okay.
So the more bonding you have, the stronger the forces are holding all the molecules together, which will in turn affect the properties of the substance. So when Dr. Stefan was talking in class, she used this example, and because of these extra bonds, H2O has a much higher boiling point than HF does, because it holds itself together better. It has more interactions between itself, so it wants to stay liquid more, basically, so you need more energy to break those bonds. Whereas with fluorine, there's only 2 bonds going on, so we can break those much faster than all 4 of those bonds. That was her point with that. Okay, so now we're going to compare some bond strength. So which is the strongest bond we just talked about? Out of those 3?
The hydrogen one.
Mm-hmm. Where do you think covalent bonds fall on the scale? Between 2 of those forces, weaker, stronger? Any guesses?
Weaker.
Weaker?
Mhm.
So if I had,
I feel like I'm wrong.
let's say CH4,
Mm-hmm.
you think these bonds are weaker?
No.
Than this bond?
Which
Which bond could I break first? Could I break this hydrogen bond, or could I break this covalent bond?
No, right. I don't know.
I think I could break the covalent bond. Because fun. If it's not fun, then
Okay, I'm glad
Okay,
we're
no.
talking about this.
no.
The reason we use dotted lines is because it is a weaker bond compared to a covalent bond. A covalent bond, these guys are sharing electrons. Like, they are physically
Okay.
bonded together by these electrons. It takes a lot of energy to break that.
Okay.
Like, think about when we vaporize something. When we vaporize water, we aren't breaking these covalent bonds. We're breaking these bonds. And then the H2O still stays together just in a gaseous phase.
Okay.
So it's not like we end up with a bunch of O- and H+ molecules in the air. We end up with water in the air. It's just vaporized.
Okay.
Which means that these covalent bonds are still intact, even though we've broken these hydrogen bonds and dipole bonds and London dispersion forces bonds. So let's put these in order then. Just to give you a sense of the magnitude of what we're talking about. So, strongest, we have our covalent bonds. These guys are sharing electrons, they're not going anywhere. Then we have ionic. Ionic is also a strong bond, but it's weaker. That's why we can dissolve NaCl in water. It's because we break the ionic bond, we get the ions, but water stays together. It's not like the water is breaking up. Those covalent bonds are still staying together. Then we've got our hydrogen bonds, which you can think of as weak ionic bonds, because ionic bonds we have a plus and a minus. With H bonds we have a partial positive and a partial negative. And then we have our dipole. Then at the very end we have our London forces. London forces, we didn't get too much into it. What is London forces referring to? Like, how do 2 molecules attract each other with London forces? What's happening with the electrons? Want to explain it for me?
I don't know.
Like when we say everything has London forces, what are we even talking about? What are the electrons doing that actually causes a bond?
They hit one another.
How do they affect one another?
It's like a chain reaction,
Uh-huh.
but I forgot what it was.
Yeah, you're right. So with London forces, if we think of a molecule, one of those cute Mickey Mouse ones that look silly. So you guys have seen molecules drawn like this, right? She's got some in the PowerPoint where it's like filled in out. Let's say it's an O and two H's or whatever. So around these nuclei, we've got a sea of electrons. I know we always think of electrons as being like attached to one of the atoms or not, but they're actually free moving, they move around, they go where they feel like it. So a London force occurs when all of a sudden, for whatever reason, statistics, probability, entropy, whatever you want to talk about, for whatever reason, more of the electrons end up over here. Not all of them, just more of them. So we get this concentration that causes a very, very, very partial negative charge. Not as strong as a hydrogen bond partial negative, just a really weak partial negative. This really weak partial negative influences this guy, which makes these electrons concentrate over here. So this is a really weak positive, and then we have a weak negative. This affects this guy. We have less over here and more over here to avoid the other electrons, so we get a partial positive. It's a chain reaction. It's so brief though. Like this happens for like nanosecond and then it disappears. However, when this is happening between thousands, millions of molecules, you get really weak bonds between each other that are charged, that are caused by these electrons for whatever reason, all of a sudden being on one side of the molecule and not the other basically. Not all of them, just more than half of them basically. It's statistics, it's a probability type thing. But all molecules display this because any of them can randomly have all of their electrons on one side.
So kind of like, we'll change the orientation of the molecules around it, I guess?
Mm-hmm.
Okay.
So it'll really briefly, I mean it's like magnets. If you all of a sudden get a partial negative here, you don't want the negative side over here, all of a sudden the electrons are going to shift over to make this the partial positive side.
Okay. So, like she said, it's a chain reaction.
It's a chain reaction. And then this one can recover, but these ones are still partially bonded because they haven't felt the effects of this one neutralizing, basically. So, super weak force. London is as weak as it comes, but it is there, which is important.
And that's called the polarizability, right? Or she talked about in class.
Yeah. So do you want, what kind of molecule is more polarizable? Give me some characteristics. So if I asked you, is oxygen, I don't know, sulfur, or iodine more polarizable? Which one's more?
Oxygen.
Why?
Because it's more electronegative.
So think about what polarizable means. Polarizable means that the electrons can move around. We already talked about how greedy oxygen is. Oxygen is crazy greedy. It wants all of its electrons pulled in real tight right next to it. It is not letting go of those things. They're going to have a very hard time trying to disperse themselves randomly, which is needed for London forces.
The iodine?
Why?
Because it's larger, so there's more
Yeah,
electrons, so
that's the big
there's a
key.
bigger probability.
Bigger atoms are more polarizable. Because this guy has, I don't know what number iodine is, he has a ridiculous number of electrons up here. Oxygen only has 6.
Right.
There's not a lot of ways to make this move to make a partial dipole. He's got, like 80, 60, I don't know. There's a lot of them hanging out there. And at any point, some of them might decide to congregate over here, randomly.
Okay.
So this applies to whole molecules too. So if I asked you if CH2 or, this is a bad example, but CH4, which one's more polarizable? CH4 is slightly more polarizable. Bad example, because hydrogen's tiny and wouldn't affect it a whole lot. But if I said like HI or HF,
HI.
definitely. HF is tiny, and that thing is electronegative like all heck. It is going to pull those electrons in and not let them go anywhere. Whereas iodine, more carefree, doesn't care where they are, they can polarize themselves and cause better London dispersion forces, which is due to a higher polarizability, basically. And when she talked about this in class, she was talking about how this can affect the boiling point too. So if we looked at, she used the example of I2 versus F2. So this isn't directly related, but it kind of has to do with that. Like I was saying, F2 pulls its electrons in real close. They aren't going anywhere. So when we talk about their boiling points, I2 has a boiling point of 184. F2 has a boiling point of negative 188. It doesn't take any heat to make it boil into a gas.
Mm.
Why is that?
Because all the molecules are together and...
So what does boiling mean? When you boil something, which bonds are we breaking? Inter or intra?
Intra. Okay, inter. Yeah.
Think about what we talked about with water. Which bonds are we breaking? Are we breaking the hydrogen bonds or the covalent bonds?
The covalent. Or hydrogen, the dot.
Why are we breaking the hydrogen bonds? Look at this, guys. Covalent bonds, they're so strong. This is strength up here. Strength of these bonds. Those hydrogen bonds are going to give way faster than those covalent bonds are.
Mm-hmm.
So when these guys break, and we no longer have these intermolecular forces, that is when we get vaporization. Because this guy is perfectly happy to stay together in a gaseous phase. It doesn't care. It doesn't want to lose its hydrogens. Oxygen wants to hang together, but once we lose this bond, it has no reason to stay in solution anymore. So why not be a gas? So we break intermolecular bonds. So think about F2. And think about London dispersion forces. So if fluorine's hanging on real tight to its electrons, how polarizable is it going to be? Very or not at all? Yeah, not very polarizable, right? Because it's tiny and it's really electronegative, and it's not letting go of those electrons, which means that we're never going to have very strong bonds. Like, even these weak London forces aren't going to be present very much. It's going to be pretty much neutral, which means that these guys have no reason to stay together. But with I2, it's got so many electrons hanging on between these two. They're not held in very closely because iodine's not very electronegative. It's a huge molecule. It can polarize itself. So if we all of a sudden get all the electrons over here and lose these guys and we get that partial negative, then we affect this guy and the electrons move over here, we're going to start getting these weak bonds. And even though they're weak, they're a bond, you know? Whereas this guy doesn't really have them at all. Which means it takes almost nothing to make F2 become a gas. It doesn't care if it's together with other F2 molecules. It'll be a gas. It doesn't care. It doesn't want to stay liquid. Iodine has these weak London forces going on, and even though they're so weak, it's impressive enough to cause this difference between boiling points. Like, that is the power of London dispersion forces. It holds things together. That kind of makes sense? Do you guys have questions about this? This is really important stuff. He's never going to ask you a super direct question about this, but it helps. It helps make things make sense. Okay, if this is kind of making sense, I think we're going to do a couple example questions. And then we're going to move on to the properties of water, which put this into context, I think. Okay, so I pulled this from your book. So we're just going to talk about it together. So I'm going to give you a compound and you're going to tell me the intermolecular forces that exist within it. So benzene. Do you guys know what benzene looks like? Once you take OChem, it's going to take over your life. It's this pretty little molecule here. probably don't know that abbreviation. The circle means that it is a aromatic compound. So it means it's got those double bonds. All this means is that it is 6 carbons attached to 6 hydrogens in a pretty little circle. So benzene, let's talk about polar versus nonpolar, because that's going to be important for deciding what kind of forces are involved. What do you think, polar or nonpolar?
Polar.
Why?
Wait, is hydrogen's attached to what again?
Carbons.
Carbon.
Oh, sorry. Yeah, sorry. This is a carbon ring.
Okay, that's what I thought.
Yes. Polar or nonpolar?
Polar.
Why?
Because it was on my lab manual today. It said, is it polar or non-polar? And well, it said, which one's stronger? And it was obviously polar. That's the only reason why. As for the explanation, I'm thinking.
Come back to your symmetrical versus non-symmetrical. This thing's very symmetrical.
Yes.
And when things are very symmetrical,
They're
what do
usually
they tend to
non-polar.
be?
Yeah.
Mhm.
But this one, I only knew that it would be polar is because of that lab manual we went.
I would double check the lab manual.
Really?
This is a classic example of a nonpolar molecule.
Wow.
Very classic. Just anything that is only hydrogens and carbon is always going to be nonpolar. Carbon and hydrogen have very close electronegativities. You don't need to know this, but I think hydrogen's like a 2.1 and carbon's like a 2.4. Super close together. Neither of them wants electrons more than the other. They share equally. Nonpolar molecule. Very classic example. So if this is a nonpolar molecule, what kinds of bonds and forces are going on within this? Give me all of them. What's holding this molecule and its counterparts together? Mm-hmm. Always, always.
Since it's non-polar, it's going to be, what was that one? I forgot already.
What else is there? There's only one other one.
Yeah.
It's real obvious. What's holding those hydrogens and carbons?
I forgot the name. Dipole, there you go.
What did he say about dipole, dipole?
Oh, was that polar?
What kind of molecules do they need to be?
Polar. Wait, yeah.
Polar.
They have to be polar. These guys have no partial charge hanging around, and if there's no partial charge hanging around, there's not going to be dipole, dipole.
Okay.
No, like, super obvious.
It was the covalent. Okay, covalent one's the non-polar.
So there's covalent bonds going on here.
I got confused with which one was not. Okay.
So those are the only things holding benzene together. It doesn't have a super high boiling point because it's only got London forces going on. Pretty standard example of a nonpolar molecule. Let's talk about CH3, Cl. If you guys can't visualize it when you see molecular formulas, always draw it. Drawing it is a really good way to see what's going on. Even if you don't draw in like the lone pairs or all the specific electrons, just draw in the basic bonds. So what are we thinking? What kinds of forces do we have in play?
This one is polar, so it's dipole, dipole. Finally got one right. Okay.
Yep, there's definitely a dipole, dipole going on. Why is there a dipole, dipole?
Because
Hydrogen carbon.
What did we talk about up here? This is a pretty non-polar bond. Anytime you see this bond, there's not going to be a whole lot going on. It's pretty neutral. The electrons just kind of hang out. They don't really care where they are between these two. Think about our electronegativity rules.
chlorine is very electronegative.
It's super electronegative. It's one of our halogens. Halogens are going to be more electronegative because if you go way back, they only have 7 electrons. They want that 8th. They're going to be pulling on electrons from anywhere they can get them. So this is going to cause a partial negative out yonder, partial positive, and then we're going to get our dipole. Yeah. What else do we have going on?
Hydrogen. No.
Are we having fun?
No, we're not. We're not having fun.
We're not having fun.
No.
What was the second one you said?
London is very.
Yes. London will always be present. And then, obviously, we have our covalent bonds again. Those are basically always going to be present. Just be aware that that's what they are. They're covalent. I think those ones are good examples. Yeah, thanks for coming. Okay. From there, we are Going to move on to the properties of liquids. So is this kind of making sense?
Yes.
I
Better
can
than
do more
before.
examples if not.
Can you give us one more example?
Something like this?
Yes.
Okay. What else do I have? What about NaCl? We talked about this guy earlier. What kind of forces do we have going on here?
This
Forces,
one.
bonds. What's present?
Oh, okay. This is gonna be dipole. So it's gonna be Wait, yeah.
Is it polar?
Yeah, polar.
Is it polar?
Wait.
No, it's not.
This is a little bit tricky because now we're getting into that other thing we talked about.
Right.
Ionic.
Oh, right.
Yeah.
Okay.
We can't forget about him. He's a very important one.
Right.
So like I was talking about, ionic is kind of our extreme dipole-dipole. Because it is our extreme dipole-dipole, we don't call it a dipole-dipole. We just call it ionic.
Okay.
It's a little tricky that way, but because you're never going to have partial charges. That's the biggest difference. You're never going to have a partial positive here and a partial negative here.
Okay.
That's just not going to happen. You have that full charge here.
Mm-hmm.
Chlorine steals sodium's electrons. Like, it doesn't leave any partial here. You're going to have the full charge.
Right.
Which is why we don't call it dipole-dipole. Dipole-dipole has to be partial.
Okay.
It's something that's free-flowing, it exchanges. This is a pretty permanent state. If you put this in water, you aren't going to have partially positive sodiums hooked together with partially positive chlorines.
Right.
You're going to have sodium ions and you're going to have chlorine ions. It's a little bit of a distinction it's good to know about, but we
Okay.
just call it ionic.
Got it.
What else do we have to have?
London.
Yes. always London. Doesn't matter what's going on. Always London. Okay, let's try one more. Okay, we're gonna compare two of them. Okay, so let's compare. We kind of talked about this earlier. So I want to know what forces are in each of these. Okay. Which forces are in both of these? Always, always. What else is there? There's our big bond. Okay, so what's different? What does one of these have? There's one other one that they both have, and there's one that one doesn't have.
Top has a hydrogen.
Yeah.
It's a bond. Yeah.
This is way too much fun, right? This one's no fun at all. This hydrogen, even though it's here, like we talked about earlier, it is not attached to this oxygen. No fun being had. So this is hydrogen bond.
Oh, got you.
So the top one's polar and the bottom one is non-polar.
So let's talk about that.
Oh.
What other force is present in both of these? We're missing one.
They're both dipole.
They're both dipole-dipole. Because oxygen is electronegative. It will be yanking on those electrons. It's going to have this partial negative hanging out there. It won't have any hydrogen bonding. Not that strong. It will have dipole-dipole. Because it will cause this partial positive, partial negative, fleeting interactions. Those bonds are there.
So they're polar, because
Yes.
they're non-symmetrical.
They are dipole-dipole. Yeah?
Okay.
You're getting a little more comfortable with it?
Yes.
I'll probably review this again next week because it's really important.
Right.
But this is what you need to be getting from Chapter 12. Chapter 12 is all about how these bonds and forces interact with each other and how they cause other things. So now we're going to move on to those other things that these things cause. Yeah?
Okay.
Alright.
Okay.
How's that covalently? I forgot.
Which one? Okay, so these bonds and these bonds?
Yeah.
Every bond that we draw a line for, if you can think about it that way, is going to either be covalent or ionic. So if you wanted to review it, it's in your book, I think it's like chapter 6 or 7. They go through covalent bonds versus ionic bonds. Ionic bonds are like NaCl. That's where they don't really share electrons. One of the ions takes the electrons and one of them's left without electrons. That's when we get our positives and our negatives. Ionic bond. We still draw a bond between them though. Covalent bond is everything else. Like almost every organic molecule definitely, but all of these other molecules we were talking about that I was giving examples with, water, I mean anything we've been talking about, fluorine 2, iodine 2, those are all covalent bonds. They're sharing electrons, basically. That's what's gluing them together, the sharing of the electrons. So even though oxygen likes the electrons more than hydrogen, so we get these partial charges, oxygen isn't strong enough to steal the whole thing away and make it an ionic bond. So they're still attached. Oxygen still has to put up with the hydrogen. It's still there. It's still donating its electrons. If you don't get that completely, go back and review it real quick from the chapter. It's not too complicated, but you should know where it's coming from. Yeah, so they'll either be ionic or covalent. Those are the bonds we talk about. Those are the intramolecular forces, so the forces within a molecule, basically. So if we say H2O is a molecule, what are the forces happening just between one molecule? Well, we've got covalent bonds. That's how they're attached. If we look at NaCl, it's got ionic bonds. That's how they're attached, basically. And then once we go from the intra, then we can move on to the intermolecular forces. And that's where we've got the H bonding happening. That's where we bring in London forces. That's how molecules affect each other. Covalent and ionic are how molecules affect themselves, basically. So that's one way of looking at it. I think I'm going to leave this board, so let's erase this one again. So, like I said, chapter 12, I don't know exactly what he's going to pull from it for the test. I'm going to talk to him about it and see if I can maybe give you guys an example problem next week. But I don't think he's going to ask you anything about crystals. If you look at the middle chunk of this chapter, there's a huge section of pages that is all about crystals and
freaked out on
lattices and covalent lattices and ionic lattices and how is a diamond made, and I don't think he's going to ask you anything about that. Peruse it at your own interest, but it's not super important for where we're going next, so I don't see him asking about it. So I'm probably not going to cover it today.
Okay.
I mean, it's kind of interesting to look at,
Yeah.
but not really. So we're going to move on to the properties of liquids. This was the last big thing that Dr. Stefan covered before we had to move on to chapter 13. This is the bulk of the chapter. This is what you should be getting from it. So there's a couple different properties of liquids that are important. Do you guys remember any of them that we talked about?
Surface tension.
Surface tension, super important. Do you remember what causes surface tension?
Capillary or something like that?
So that's a result of surface tension.
Okay.
But what causes surface tension? Why are there those bugs that can walk on water? Why is there surface tension at all?
Because
It has something to do with these guys.
Just kidding. No bonds.
they stretch the.
No, you were close to the hydrogen bonds.
Oh.
Yeah. That's a little bit.
Adhesion, cohesion.
So that's kind of it. That's a little bit more capillary action like you were getting into.
Oh.
Surface tension itself, the molecules are getting pulled together. Water, perfect example, has great surface tension. Why does it have great surface tension? Because these molecules want to stick together. They hate air. If you look at water, you've got air up here, and you've got liquid down here, and these molecules are all trying to hydrogen bond together to get as far away from this air as it could. It wants to stick together. It can't bond with the air. It can't do anything with it. I mean, if you look at water, it basically bunches itself inward. That's why you get drops of water. Drops of water on any surface, you don't get like little dots of water, you get drops of water. You get that because of surface tension, because they want to stay together. They love hydrogen bonding with each other. It's fun.
Right.
That is what they like doing. So that's because of surface tension. It's usually hydrogen bonds. It's usually water when we talk about these properties of liquid. Usually we mean water when we say that. So water loves its surface tension. It loves hanging on to each other. That's why really small bugs can walk on it. That's why we get drops of water. That's what causes these other properties we're going to talk about. This kind of wanting to stick together.
Right. These
strong intermolecular hydrogen bonds.
So in a way, it's like a blanket, like when something, like a bug is walking, or they're just like, hey, no. Like,
yeah, it's
okay.
trying to force air out. It doesn't
okay.
want to involve itself with anything else around it.
Right.
Water likes itself, basically. That's why you get circles, because do you know what a sphere is?
Yeah.
A sphere? Well, I know you know what a sphere is.
Oh.
I was just like,
Okay. No, do you know like the specialness of spheres? Like volume compared to area?
Something about the radius or something?
A sphere is the largest volume with the lowest area that you can get.
Right.
So it's holding the most stuff for the least amount of surface area, which is what water wants to do. It wants the least amount of surface area so that everything can be involved in the volume and be involved with each other. Like side math note, but that's why it does it. It's because there's less surface area. It doesn't have to interact with air as much. That's why we have water drops.
Right.
They're spheres. Okay, so then we can move on to capillary action, like you guys were talking about. Capillary action is caused by very similar things to surface tension. It's caused by these hydrogen bonds. Capillary action is all about, like, I don't know if you guys have ever used like the capillary tubes. If you stick them on a drop of water, water shoots up that tube. Even though it doesn't make sense, right? It's opposing gravity. Water shouldn't shoot up a tube. It's because it wants to stick together. Once one drop gets pulled in, all the drops want to be pulled in. They're trying to stay with each other. Those hydrogen bonds are stronger than gravity, basically, at that point. This is why plants survive, in case you guys are biology people. This is why plants work. Trees suck up water through capillary action. That's why they can have leaves up top. Super, super important. And then under capillary action, we get into cohesion and adhesion, which are basically just subheadings of this. It's not super important that you remember, like, these definitions, but just to be aware that there are two different types. Cohesion is when two like molecules are attracted to each other. So this is between two like molecules. And I'll give you examples of these. But and then adhesion is between two different molecules. The kind of standard example is what she was telling us in class about how you can look at water or mercury in a tube. So if you look at mercury, mercury displays cohesion. Mercury would much rather bond to itself than to glass. So with mercury, what we get is we get this convex bubble because it doesn't want to be touching the side. Mercury would much rather clump up here attached to itself than it wants to be touching the surface. Water is the opposite. If you've ever been in lab and you've looked at water in a beaker and it does that stupid meniscus thing, that is due to adhesion. That is because water wants to bond to silicone. It likes silicone. It would much rather bond with that than to itself. So it creeps up the side of the tube and makes reading measurements a lot harder.
Okay.
So it does have a weakness sometimes, water.
Yeah. Water can be attracted to other things more than itself. It's just not air.
Oh, okay.
Yeah, no, silicone is what water wants to be, and that's why we get these meniscus things. That's adhesion. That's water liking silicone better than itself. So just something to be aware of. Not something that you're probably going to get directly tested over, but it's interesting, good to know in your lab. Hey, look at that adhesion going on. Could be fun.
So for our test, is it like all calculations?
Dr. Kinnade's tests are very calculation-based, which is why this is going to be hard for him to test. He doesn't do multiple choice. He doesn't do a lot of concept questions. he's a big fan of if you know how to work a problem, then you have to understand what's going on.
Right.
So what I'm doing today is trying to fill you in on what's going on, and then next time I'm hoping to move on to chapter 13 and actually get into like some practice problems and really get down to the calculations and what he's going to test you on. Like I'm saying, I've got to talk to him and figure out what he's going to test over chapter 12. We'll see though. I could see him giving you molecules and asking what forces are going on. That's very typical of him. I remember questions kind of like that, where he'd give you a bunch of molecules and then he'd say, what's going on? Like, tell me which of these 4 things is happening within this molecule kind of thing. So, that I could see him doing. I'm going to talk to you about it. We can figure it out next week. So, yeah, they're very calculation based. Very similar to your quiz. Like, he's completely right in saying his quizzes, his tests are just like 9 times that, basically. On that note, he's not kidding. His tests go by fast. I'll probably talk about this more next week when we actually get to test time, but you gotta keep moving. Like, if you're a slow test taker, you gotta make yourself keep moving. No staring at one problem for 10 minutes, because then you won't be able to finish. Because he's only got 50 minutes. Like, it's not a long class. So, we'll talk about that more next week, but just be aware.
So pretty much like 10 minutes per
I
problem.
mean, I don't mean to scare you, but you need to be aware. Like, you are not going to finish this test if you dilly-dally. You just won't. So, something to be aware of, not meant to scare you. We'll go over it next week. I have practice tests. Okay. The last 2 things in properties of liquids were viscosity and vapor pressure. So let's talk about viscosity real quick. What is your guys' understanding of viscosity? What does that mean to you?
Resistance probably. Kind of like honey.
Exactly. Okay. So is honey high viscosity or low viscosity?
High.
Because it doesn't like to flow. It's a perfect example. I said syrup, but honey's even better. So water has a low viscosity. That's basically the gist of it. I mean, things that are very viscous don't want to flow as much. They'd rather stay where they are. They'd rather not move. Low viscosity things don't care where they are. They're what we think of as our standard liquids. You know, the things that take the shapes of the containers they're in, basically. Something just to be aware of is that more viscous things have greater intermolecular forces. So it's just one of those things. Like, water's not a great example because water is a special liquid that has a lot of things going on that we haven't talked about yet. But if you think of like honey, like we were talking about, honey's going to be a liquid that has a lot of intermolecular forces going on. There's a lot of bonds happening. There's bonds that it doesn't want to break. That's why it doesn't want to move. Whereas if you think of something like benzene, if we go back to our benzene, which is benzene polar or non-polar?
Non-polar.
Yes, it is non-polar.
I took a picture of it. It literally says which one is polar than the other. Like, and it's benzene and benzoic acid. And so basically they said they're both polar. I'm just like, okay.
No, benzene's definitely non-polar.
Wow.
So benzene in solution is going to be not viscous at all. Like if you compare water to benzene,
you're right.
Benzene's even less viscous than water.
Oh, wow.
Like benzene will flow better than water will because it doesn't have the hydrogen bonds slowing it up.
Oh.
It only has London forces, and like we talked about, they're not that strong. So it doesn't care where it is. It'll flow wherever you want it to flow. The other thing is, if I raise the temperature, is it going to get more viscous or less viscous? If you think about it.
Less viscous, because let's say you melt honey, and my dad does this all the time. Yeah.
I always think of syrup on pancakes.
Yeah.
Like, if you heat up your syrup, it's going to become a lot less viscous.
Yeah.
Try heating up syrup sometime. It's going to become watery.
Yeah.
Like, it's going to become way less viscous because there's a lot of heat interacting, and the heat is breaking the hydrogen bonds faster than it would be if it was cold. That's the example I think of when I'm trying to decide what's happening. There's no formula you need to know to go with this, but just know the pattern. Higher temperature, lower viscosity. It's easier if you think of examples. Like, if you can't think of anything else, melting butter.
Right.
Like, not a great one because it's going from solid to liquid, but, you know, margarine can be in that semi-liquid phase. Syrup's my favorite one, though. So.
Yeah.
Okay, we're on our last one. Vapor pressure. vapor pressure is also super important to be aware of so that we can talk about boiling.
Okay.
So when you think of vapor pressure, what do you think is happening? Do you have any ideas? What does vapor pressure mean?
Liquid to gas, evaporation, all those things.
Mm-hmm. Yep. So if we have a beaker filled with a liquid of your choice,
Mm-hmm.
it's going to have some molecules at the surface that randomly get enough energy to vaporize. Like, it's why evaporation occurs. Evaporation is an example of vaporization in process. So some of these molecules are going to get enough energy to become a gas. Which means that right above this surface, we're going to have a layer of gas particles. This pressure is what vapor pressure is referring to. It's this pressure of gas particles right above the liquid that occurs spontaneously. So we're not doing anything to it, it's just sitting there, but it's going to have some up here. Some of them are going to lose energy and they'll fall back into solution, but it'll hit an equilibrium where we have some pressure of molecules right above it that stay there. Even if it's going in and out, it's in and out at the same rate, causes a standard vapor pressure. This is important just mostly because of boiling point. So this vapor pressure can go and define boiling as point. So do you guys know what the definition of boiling point is? When do we hit boiling point? How do we boil something?
Heat it up.
Mm-hmm.
Is it 100 degrees Celsius?
For water.
Yeah.
The trick there, though, isn't that it's 100 degrees Celsius.
Oh.
It's 100 degrees Celsius at 1 atmosphere,
Well,
which has
Oh.
everything to do with pressure. So boiling point actually has less to do with temperature in its definition than it does to do with pressure.
Oh, okay.
So what definition of boiling point is, it's the temperature at which the vapor pressure, so the amount of molecules in gas above it,
Mm-hmm.
because if you heat this up, it's going to get a higher vapor pressure. More molecules are going to be in gas above it, right?
Right.
So boiling point is when the temperature is the temperature at which vapor pressure equals atmospheric pressure. So 100 degrees Celsius
Mm-hmm.
is when water is at 1 atmosphere,
Got it.
if that makes sense. So
Yes, that
this
does.
chunk right above it equals 1 atmosphere.
Right.
So at that point, it can start boiling everything up into the amount of pressure that's there, basically. So it equals atmospheric pressure. It's kind of a weird definition. It's okay if you have to think about it a little. But what it means, basically, it's the amount of heat it takes for this pressure up here to equal the pressure around it. Because usually it's less than atmospheric pressure. Usually this will be like a third of an atmosphere, if not less. Like, it's not a lot of pressure happening there. But when we can make this reach the atmospheric pressure, then it'll stay in the atmosphere. It won't feel the need to go back into solution, basically. So if none of it's going back in solution, but things are still going out of solution, eventually it'll all be vaporized. A little bit of a weird definition, but it completely relates to vapor pressure, and then of course vapor pressure totally relates back to intermolecular forces.
Mm-hmm.
Because the more intermolecular forces you have, the lower the vapor pressure is going to be.
Okay.
Let's go back to water. Water wants to stay together. It doesn't want to be in the air.
Mm-mm.
It's going to have a lower vapor pressure than benzene.
Mm-hmm.
Benzene has a pretty high vapor pressure. It doesn't care if it's in solution or not. It's nonpolar. It doesn't have hydrogen bonds. All it has is London forces.
Right.
So if you compared benzene to water, water would have a much lower vapor pressure because it doesn't want to leave itself, basically.
Right.
Its hydrogen bonds are holding it together. It doesn't want to go into here. That's why it has such a high boiling point. 100 degrees Celsius is pretty high.
Oh, okay.
So that's kind of why that happens. And that's also why if you go to the top of a mountain,
Mhm.
you don't have to reach 100 degrees Celsius because lower atmospheric pressure.
Mhm.
If you're in somewhere where it's only half an atmosphere, then you only have to reach half as much heat, kind of thing. I don't think it's a direct correlation, but it's significantly lower. It's like 70 degrees Celsius instead of 100 because there's less atmospheric pressure pushing down on the molecules.
Right.
So it'll leave solution faster. Yeah?
Yeah.
Got it.
I know this is a lot of material. I'm trying to cover one chapter in a day, which is a lot.
Right.
We only have one last thing to cover though. We're going to talk
Okay.
about phases. Who loves phases? This is also something that I see as very testable.
Okay.
It's phase diagrams are something that you could easily throw in a problem and ask you guys to do something with.
Okay.
So, but it builds on what we've been talking about. So what is a phase diagram or a phase chart, or what's it showing us?
From a liquid to a gas, solid to a liquid to a gas.
Yeah, so it's showing our different phases, right? There's a lot of different ways to display this. I've got 3 different ways. So we're going to start with kind of an arrow graph that was in our PowerPoints. So as temperature increases, I've got cute little arrows to go along with this. Okay, so each of these arrow lines, besides temperature, has a name associated with it. So we're going to go through and name everything. So if we're going from a solid to a liquid, sorry, that's where that's supposed to be. Solid to a liquid, what is that phase change referred to as?
Evaporation.
Ding, ding, ding! Melting!
Okay. Oh, right.
Makes sense.
I'm not trying to trick you, I promise.
I was thinking too hard.
Melting, very non-scientific. You can also call it fusion if you're feeling into it. It's another way they can refer to solid to liquid phase change. Ta-da! Add temperature, solid to liquid, called melting. Okay, what about liquid to gas?
Evaporation.
Let's use a more general term.
Vaporization?
Oh, there you go.
Yep, if we're vaporizing something, we're going to the gaseous stage. Vaporization. Okay. Oop, that's going the wrong way. What if we go straight from a solid to a gas? You guys know what that's called? If you've ever played with, like, maybe some, like, liquid nitrogen. Ah, yes, sublimation.
Oh,
I
that
have to
term.
pronounce
Sublimation. It means going straight from a solid to a gas. You're giving that solid so much energy so fast, it skips the liquid phase.
Like, can you give us an example?
Liquid nitrogen. Have you ever been at like a Halloween party and they've got a drink with like steam coming off it? That is, I think that's actually frozen carbon dioxide. But liquid nitrogen also does it.
Okay.
So, frozen carbon dioxide, you get like these big chunks of ice and you stick it in the drinks. And it looks really cool because there's like steam coming off it. But what that is the frozen carbon dioxide doesn't want to stay, because carbon dioxide's a gas at room temperature, right? It doesn't want to be frozen, it doesn't want to be a liquid, it wants to be a gas. It goes straight.
Okay.
We don't talk about it a lot because we don't usually use things that sublimate, but it's there. Solid to gas. Good word to know. What about gas to liquid? Happens on the edge of your glasses. Condensation. Gas to liquid. Just think about a cold drink, hot summer day. We've got condensation on the outside. Okay, what about liquid to solid? I know you know it.
Oh, yeah, please. I'm so happy.
This one's a little harder. Gas to solid. Anyone know what that is? Anyone been
Decomposition.
reading up?
Okay.
Actually, close.
Deposition.
Deposition. Yes.
I read all this. It's been a while.
Deposition.
Yeah.
You will probably never hear that word again in this class. I can't even think of an example. I have no idea. You will probably never use it again. Some fun Jeopardy word, I don't know. You can know it for the future. This wasn't your PowerPoint though, so I figured we go over it. Just the different changes between our different states of being.
So that'll be in the test, more than likely?
I don't think so. We're getting to the thing I think is going to be in the test.
I was like,
Yeah.
okay.
We're progressing there. Okay. So then there's another way that we can show a very similar concept. I'm sure you've seen graphs like this. So our x-axis is the amount of time we've been adding heat. And then this is our temperature over here. And then we get a cute little graph that looks something like this. Does anybody recognize this? Kind of?
Yes.
What kind of matter do I have right here?
Solid.
What about here?
Liquid.
Uh-huh.
Gas.
Yep. You got it. So,
Superficial
what's this
point.
temperature right there?
Um,
You'll see the dotted lines drawn across like this in the temperature graph.
I think right there it's 0. Or wait, no.
It's not a temperature,
Mhm.
it's a name of something.
Oh.
So what do we get between a solid and a liquid? There's a temperature that's really important. It's 0 degrees Celsius for water.
No.
Nothing.
No.
Nothing.
Put it together.
Melting point?
Yes.
Oh.
This is your melting point.
Once you see the graph, you'll know what.
Okay.
Can we guess the top one now?
Freezing point?
Yeah.
Mm,
Wait,
Just
what?
kidding.
Try again.
Vaporization.
Liquid to gas.
Okay.
Liquid.
We were
Condensation.
just talking about it. 100 degrees Celsius.
Boiling point?
Yes. This is where
Okay.
we boil things. So, freezing point is an interesting thing to say because where's the freezing point on this graph? It's there. Where is it?
No. Wait,
Where are things freezing? Which temperature? Think about it.
It should be right.
So it'll be the bottom.
Solid. Okay.
Where? Here?
Yeah.
Right.
How about here?
Um,
This is also called your freezing.
Alright, okay.
Well, let's think about it. Let's talk about it.
Okay.
What is a freezing point? A freezing point is the point at which your liquid starts becoming a solid, right?
Mm-hmm.
What's your melting point? Your melting point is the point where the solid starts becoming a liquid.
Liquid, right.
Oh.
This line here
Oh.
is where you have liquid and solid existing.
Mm.
It's the temperature at which it hasn't made up its mind yet which way it wants to go. It needs to have more heat added or taken away in order to decide.
Okay.
That's why it's your freezing point and your melting point. When we get further in the class, we're going to talk about, well, we started to already, actually, boiling point depression, no, freezing point depression and boiling point elevation.
Mhm.
Have we talked about that? I thought we got to it a little. No? Okay, we'll get to it later. We don't use the term melting point ever in science. It's your freezing point.
Okay.
But it's also called your melting point, because that's what it is. We could also call your boiling point your condensation point, because that's the point at which you get gas to liquid. We just don't call it that.
Oh, I see.
This line is where liquid and gas exist together. They're coexisting, they haven't decided which way they want to go yet.
And the end part is the superficial point.
Yeah.
Yeah.
We could get into, there's like plasma up here somewhere, but we're not going to
Oh,
get
okay,
into that.
gotcha.
So, these are the importance of these. This actually is not what I think he's going to test you on either, but these are
Okay.
super important to recognize. He might, I have no idea.
Okay.
It's important to recognize what this graph is telling you.
Right.
If he gave you this graph and said, this is the graph for, I don't know, methane,
Mm-hmm.
and he gave you a scale here, and he said, what's the melting point of methane?
Right.
What you would do is you'd look at this line, and you'd go over and say, oh, it's 20 degrees Celsius, 30
Gotcha.
degrees Celsius.
Oh. Okay.
You look at this line, and you go over, and you say, well, of course the
Boiling
boiling point is X.
Mm-hmm.
You should be able to read it. I don't think he'll make you label it, but you need to be able to read it and say, oh, well, here's the melting point. Here's the boiling point. That kind of thing. Unfortunately, we are out of time. The last thing I was going to cover was phase diagrams, but I guess I will have to do that next time.
All right.
Do you guys have any questions?